Hey guys, in the last lecture we talked about trying to find integrals of functions that happen to be compositions. We used u substitution in that case. In this lecture we're going to deal with functions which have an interesting property. They have the property that the product of the derivative of one of the functions times an antiderivative of the other function is easier to integrate than the original product. So that might seem a little bit weird, but let me write out a couple of examples to show you potential uses for this, and then we'll see how we can deal with these. So this topic is integration by parts. And before I tell you how to do integration by parts, I want to give you some examples of structures that we're looking for. So what to look for? So here would be some examples. The integral of x times e to the x dx. So as I said, the integral of the derivative of one of these guys times the antiderivative of the other is easier than the original function. So what am I talking about? Well, the derivative of x is just 1. If I multiply that by the antiderivative of e to the x, that's just e to the x. That's something that I can integrate. If my product has that property, integration by parts is something that will help you. So that's one example. Another example, integral of sine of x dx. Again, don't know how to integrate that, but I do know how to integrate the derivative of that, which is 1, times the antiderivative of that. Similarly, x times cosine x. So again, it's a similar situation, derivative of that times antiderivative of that, I can do. A couple of others which aren't so obvious. Natural log of x. So we don't have an antiderivative for this guy. I don't even see a product here. But if you think about it, there is a product. I can multiply this by 1. And the derivative of this is just 1 over x. Antiderivative of that is just x. And that's something I can definitely integrate. The integral of x times 1 over x is just the integral of 1. Analogously, 1 times arc tangent of x. So if I wanted to integrate arctan of x, I'm thinking of it as that product. And even if I can't integrate this guy as it is, derivative of that is 1 over 1 plus x squared. Antiderivative of this guy is x. And this is something that I can integrate using u substitution. So when things look like this, we know integration by parts is going to work. Again, we don't know how it's going to work just yet. I'll do that in just a second. Let me add a couple of comments. So x squared times e to the x, or x squared, would also be a great integration by parts candidate, because if I take the derivative of this, I get 2x. Times the antiderivative of that is e to the x. And even if I can't integrate that straight away, I could still use this parts process because we already said that x e to the x is a candidate. So in other words, sometimes you'll have integration by parts twice. In fact, we need to keep our minds open to the idea that sometimes you use multiple integration techniques to solve problems. So this was another example. We used parts, but we're also going to use u substitution. So let me also say that, and this is a little bit subtle, and you'll start seeing it when you start doing some problems, which is I said, hey, the integration by parts is going to be good if the derivative of one times the antiderivative of the other is easier than the original function. Another thing to look for, which is a little bit more subtle, is that the derivative of one times the antiderivative of the other is no more difficult than the original integral. So let me just throw that out there, and when you do some homework problems, you'll probably see what I'm talking about. All right, so how the heck does this thing work? We know what to look for, but we don't actually know how to solve it. So let's study this guy. And let's realize that this guy is a product. So I'm going to start looking at the product rule. So just start looking at the product rule that we learned in differential calculus, and I'm going to see if that might be able to help me. So as a reminder, that's first times the derivative of the second plus second times the derivative of the first. So that is the product rule. But if that's true, then u of x times v prime of x, so this guy here, is going to equal, well, let me subtract this from both sides. Actually, I think what I'd like to do, I want to keep this here. So I want to move, yeah, I want to move this guy to this side, but I'm actually going to put them both over here. So in other words, let me write this as the derivative of u of x times v of x minus v of x times u prime of x. So in other words, I move this guy over here, and then I just put this on the left side. You'll see why in a second. Right? If you believe that, if those guys are equal, then I can integrate both sides, and equality should be preserved. So I'm just integrating across. Integrating each of these terms. We know we can do that because the integral of a sum or difference is the sum or difference of the integrals. And then I notice that I'm integrating the derivative of something. Well, if you integrate the derivative, you're going to get the original function back. The integral of the derivative. We're finding an antiderivative of the derivative. So we're getting this guy back, minus the integral of v of x times u prime of x dx. So why does this help? Well, remember, what am I actually integrating then? So I start with this, u of x times v prime of x, but instead of integrating that, I'm integrating the derivative of one of those guys times the antiderivative of the other guy. Can you see that? The derivative of one times the antiderivative of the other. And we already said that we know how to do that with this guy. So before I do that directly, let me tighten up this formula in the way that it's typically written. And it's typically written by suppressing the x values. So some of you may have seen that suppressing the x when you did implicit differentiation. But if you haven't seen that or you forget what it is, we're just going to not write x, just to tighten everything up here. So instead of u of x, I'm just going to write u. And instead of v prime of x dx, thinking back to u substitution, I'm just going to call that dv. So that whole thing, I'm just calling it dv. So the integral of u dv is equal to u times v minus the integral of v du. So that's the integration by parts formula. So how would this work in our particular example? So basically, I need to decide u and dv, and then I'll plug it into my formula here. And how do I decide this? How do I decide this? What I'm going to do is I'm going to let u be the thing and dv be the thing such that u prime times v is easier than the original product here. So if I let u equal x and I let dv equal e to the x dx, again, I'm matching up my parts visually. It should feel like u substitution. Then once I do that, du is u prime of x dx. So in this case, it's 1 dx, or just dx. And if dv is equal to e to the x dx, if dv is equal to that, then v is going to be my antiderivative, or e to the x. So I'm just trying to get all of these pieces that I need on the right-hand side. Well, according to what we did here, which in some sense is a reverse of the product rule, This tells me that this integral, put it over here, is equal to u times v, or x, e to the x, minus the integral of v du. So notice, in this formula, we have exactly what I talked about at the beginning. Hey, I can't integrate x e to the x, but I know how to integrate the derivative of this, aka 1, times the antiderivative of e to the x, aka e to the x. So the thing that I'm integrating is the derivative of 1 times the antiderivative of the other. So this becomes x e to the x minus the integral of e to the x, which is e to the x, plus c. So let's do another example together. Let's try the integral of x times sine of x dx. And again, the parts formula is u times v minus the integral of v du. And the way that we're going to solve this in an organized fashion is we're going to let u equal one of those guys. We're going to let dv equal the other guy dx. So we're going to do that the same way every time, and then we'll be able to plug it into the formula. So stop the video for a second. What do you think u should be? What do you think dv should be? Again, whatever you let u be is the thing that you're going to take the derivative of in your formula. Whatever you let dv be is going to be the piece that you're going to use as an antiderivative in your formula. So stop the video for a second. Think about it. So hopefully you said, let's let u equal x and dv equal sine of x dx. Why? Because the derivative of x, which is 1, times the antiderivative of sine of x, which is minus cosine of x, 1 times minus cosine of x is easier to integrate than this original guy. And in this formula, that's what I would have to integrate. Well, let's see it. The derivative of this happens to be dx. If dv is sine of x dx, then v is going to be equal to minus cosine of x. And then we just follow our formula. So this is equal to u times v, or x times minus cosine of x, u times v minus the integral of v du. Perfect. This is something I can integrate. Again, this guy is the product of the derivative of 1 times the antiderivative of the other. This becomes minus x cos x plus, integrating that, we get sine of x plus c. Right, and as a final example, let me leave that up on the board so you can check it out as we're doing the final example. The integral of the natural log of x. So again, this one's a little sneaky because I don't see a product, but if I write it like this, I do have a product. And I know the derivative of ln of x is 1 over x. I know the antiderivative of 1 is x, and 1 over x times x is something I can integrate, which tells me parts is going to work. So again, let me give you a minute. Decide what is u and what is dv. Right, hopefully you said that u is ln of x and dv is 1 dx, or just dx. Then du is 1 over x dx. V is x. So then we have, let's see, u times v, or x ln x, u times v minus the integral of v du. So that's the integral of ln of x. So this is just x ln x minus the integral of 1 dx, and that's just x ln x minus the integral of 1 dx is just x plus c. Boom. If you take the derivative of x ln x minus x plus c, you're going to get ln of x back. So that's integration by parts, and in summary, if you can find that your structure is such that you have a product of things, or a hidden product of things, and the derivative of one of those guys times the antiderivative of the other is easier to integrate than your original problem, or no more difficult, then it's a candidate for integration by parts.